In reference to what we just did in the last video, this is the nice graph going through, but never getting close to 2, but never going past 2, and crossing at 3 instead of 1 because it's been shifted over 5. This is Euler's constant. I know it looks like Euler, but it's Euler, and so there's that. Then I want to introduce the inverse tangent function. I don't think I've formally done this. I've done sine and cosine, but you can see that it fails the horizontal line test badly. Here's a horizontal line, more or less, and it fails. So what we do is we use the same limitations as we do for sine. We go from negative pi over 2 to positive pi over 2. And whereas sine can actually equal those limiting endpoints, tangent can't, because if you notice for the tangent, they're asymptotes. So I'm never actually going to be able to equal negative pi over 2 or positive pi over 2, but I have to stay between. So figure 17 here shows where they just took that one piece of the tangent function, and we're limiting ourselves to that, okay? So if we were going to draw a circle, we just are limited to this half circle, okay? We can't go over into quadrant 2 or 3 because, well, we're saying that it doesn't exist there. Also, you might want to think about the fact that you're not surprised that we can say y equals inverse tangent x, means that x equals tangent y, because we know when we look for arctan, we're looking for an angle, so y must be an angle. And you can see y is limited to these right here. And so our range, we have to say our range is unlimited, okay, because as you can see, it goes up here and it goes down here a long time. So the range is unlimited. The domain, which seems kind of backwards, is from negative pi over 2 to pi over 2, and not including the endpoints. So here, this book shows a table, but I don't think we need to memorize a table. I think we can just do our normal thing. We know we're limited to this side of the graph, okay? So if they ask me to find the tangent equals 1, I would say, oh, I seem to remember a triangle a while back. Let's see, it looked like this, and it had 1 over 1. That's the tangent, right? So if this is my theta, then I'm pretty sure the hypotenuse is the square root of 2, and I know what that angle is. It's theta equals pi over 4, just because, well, it's 45 degrees, or pi over 4, because, this is my 45, 90. Now the same thing down here with the second example. We have our graph, and we know we can only be in quadrant 4 or 1. And since it's negative, we're going for quadrant 4. And we say, the opposite side is the square root of 3, and it's negative, of course. It's down there. And let's see, do I know any triangles like that? Yeah, sure I do. The tangent is the opposite over the adjacent, so there we go. And so then I know from my reference triangle that the hypotenuse is 2. And I know what this angle is. This is 60, or pi over 3, but I'm in quadrant 4. I could say that theta is equal to, let's see, we're divided into 3, so I could say 5 pi over 3, but I'm not allowed to go through 2 and 3, so I better not say 5 pi over 3. I better say negative pi over 3 and go directly there. Take away the 1 pi over 3 instead of going 5 pi over 3. Same thing on the coordinate plane. 3 on the top, 3 on the bottom. I go 5 of the 6 total. 6 pi over 3 is 2 pi, right? That's the total. Okay, so if I went 5, I'd get to the same place, but I can't go 5. I'm supposed to go down 1. So I have negative pi over 3 because I'm limited. I can't do the other. But I still know what I'm talking about. And I don't really need this chart. I suppose you could memorize the chart, but I know reference triangles, so I don't need to. And then, let's see. I threw in the sine review because your problem involves a sine, an arc sine. Okay, so let's see here. We're going to write this trig expression. And we're going to say, well, let's see. First of all, the arctangent of 2x, that implies a triangle, right? There's some triangle where the opposite side is 2, must be, right? Well, 2x, right? 2x. And the adjacent must be 1. Okay? So I know it doesn't look like it says 2x over 1, but it is. It's always over 1. So then I think, well, Pythagoras tells me how to find the hypotenuse. Let's see, I square this one, and I square this one, and I take the square root. So I say the hypotenuse is 4x squared plus 1. Okay. So I know the dimensions of the triangle, and I'm going to use that triangle because here we go. That's my angle, and it's a 90-degree triangle. Okay, so the other one says arc cosine, or I could just say cosine minus 1, inverse cosine of x. And so let's see, this is positive, and I'm in quadrant 1. I better be in quadrant 1. And let's see here. It says the adjacent is x, and it's over 1, so the hypotenuse must be 1. So I say to myself, let's see, there's a relationship here where c squared is equal to a squared plus b squared. And I don't know b. Maybe I shouldn't write b because I'm going to fill that in. So let's see, I say to myself, b squared is equal to c squared minus a squared, and of course I want the square root, and I say b is going to equal the square root of c, which square root of c squared, which is 1 squared, minus a squared, which is x squared, and I think that's the best I can do for this side over here. It's 1 minus x squared. All right, so that's my opposite side. Okay, so now I'm ready to go. With these two triangles all set up, I know what I'm talking about now. Before I wasn't quite sure, but now we know, and we should write that out. So we'll say we know that sine of u minus v is equal to sine of u cosine of v negative cosine of u sine of v, right? Okay, so let's see, we're going to say the sine of arctangent, let me just say inverse tangent, times the cosine of the arc cosine, or the inverse tangent of x, minus the cosine, I messed that up, didn't I? Sorry. The cosine of the inverse cosine of x minus the cosine of inverse tangent 2x sine arc or cosine, inverse cosine x. Maybe that was too confusing to change it to the -1 inverse idea. Okay, so anyway, in the meantime, let's see what we have here. We have the inverse tangent of 2x. So the question is, what angle am I implying there? And the answer is, I know what angle it is. Okay, we're gonna call this angle U. Okay, that's angle U. I don't really care what it is, you know. Unfortunately, don't really care what it is. This is angle V. So, you know, as long as I have that, I guess I could just write sine of U. I could go back to the, because I really don't care what these angles are, to tell you the truth. Right? Not really my business. Because I'm just going to do something with the angle anyway. So now that I know what U is, what is the sine of U? Well, let's see. The sine of U is 2x over the hypotenuse, which is the square root of 4x squared plus 1, times the cosine of V. What's the cosine of V? Well, that's times x over 1, minus the cosine of U. What is the cosine of U? Well, that's 1, the adjacent over the hypotenuse, 4x squared plus 1. And what's the sine of V? Well, let's see. The sine of V is the opposite, which is the square root of 1 minus x squared over the hypotenuse, which is 1. Okay, so it's nice we have a common denominator. So when we multiply this together, so we're going to have 2x squared minus the square root of 1 minus x squared, all over the same denominator, 4x squared plus 1. And then I think to myself, you know, I know I should really get rid of that radical on the bottom. I should. But you get the idea, right? That's the idea. Okay? So, did I really care what the angles were here? No. U is something. I don't know what it is. V is some angle. I don't know what it is. I don't have to care. The inverse functions on the inside of the parentheses imply some angle. And then the sine and the cosine on the outside of the parentheses, they use that angle to get something in terms of which I do not know. I don't know what x is. But, you know, I never actually had to know the angle to find this. I just used it. Once I found out, once I drew the triangles, that was good enough. I used the angle in its position to find out what they wanted to know. And if I was a glutton for punishment, I'd go ahead and get rid of the radical on the bottom. But we've already practiced that today, so I think that's good.